In today's lessons, we will learn about the new chapters, which is fuzzy logics. So fuzzy logic is a bit different in contrast with the artificial neural networks, in which for the artificial neural networks, you need to rely on samples. You need to have many samples in order to tune the model properly. However, in contrast with that, fuzzy logic does not need any samples, but it more relies on the membership function in order to tune its model. So the better you tune the membership function, it will make the system much more optimal. So what you will learn from the fuzzy logic aspect is, first thing is what is the fuzzy logics. Second thing is why we use fuzzy logics in our system. Then third thing is, the most important thing is how you can use fuzzy logics to develop some real applications. So first thing first is, what is fuzzy logics? So in general, fuzzy logics comes with the words of fuzziness. So according to the English Oxford Dictionary, fuzzy means that blur. So the opposition word will be clear, crispy, or something like that. So in Malay, fuzzy means kabur or sama or kurang jelas. So it's quite clear to you, means that fuzzy means that the things that you want to model is a bit gray from the crisp function. So for more details, I will go step by step in order to ensure that you can understand the concept better. So fuzziness is the deterministic uncertainty. Deterministic uncertainty means that the uncertainty models can be constructed by using the mathematical formulations. Fuzziness is connected with a degree to which event occurs. So means that for the fuzzy concepts, the event is already occurs, but with how many amount of occurrences. So in contrast with the concept of the probability, means that the event is not yet occur, but you just predict. So how many occurrences or how highest probability that the event will occur. So there is the different concept between the fuzzy and the probability. So to make the things better, much more understandable, so let's watch this video.
So what is fuzzy logic? Well, first let's think about traditional logic. In traditional logic, something can be represented by either having a value of true, which is 1, or false, which is 0. In fuzzy logic, you can be anywhere in between 0 and 1, so you could have something that's true, but only partially true, with 0.7, or false, it's mostly false, with 0.3. So let's use tap water temperature as an example. In traditional logic, you would have this represented by either being hot or cold, representing 0 or 1 respectively. With fuzzy logic, you could have something like this, where you have a gradient from hot to cold. So you could have something that is lukewarm, very hot, slightly cold, etc., instead of just hot or cold. So why is it useful? Well, consider you have an automatic braking system in your car that can decide when to brake. Using traditional logic, it might look something like this, where you have a car in front of you that's far away or close, and there's some value in between where it switches. The car being close can either be yes or no, 0 or 1, and the brakes can either be on or off, again 0 or 1. So in this situation, the car is far away, so it's not close, and the brakes are off as a result of this. Now in this situation, the car is now close, represented by 1, and the brakes are now represented by 1 as on. Now this might be a problem because the car is now applied the brakes with full pressure, and you're going to slow down very quickly, even though the car in front of you might not be approaching you very quickly, it might not be moving at all. And this puts huge stresses on the car, including the components like the suspension, the frame, not to mention the occupants. So instead of doing something like that, let's consider using fuzzy logic. So this is your situation, and now, going from close to far, you have this gradient. And you can say, is the car close? Well, it's anywhere between 0 and 1, this range. And the same thing with the brakes, you can apply pressure between 0 and 1. So in this situation, is the car close? Well, 0.2. It's not very close. And as a result, the brakes, we're only going to put slight pressure on. And in this situation, is the car close? 0.8 is pretty close. And as a result, the brakes, we're going to apply fairly heavy pressure to. and this will slow us more quickly. The result of this is that you get a much smoother output depending on where the car is, and it's not just on or off for your brakes. This will put less stress on the car and the occupants. So how is it different? Well, with traditional controllers, you need to know detailed physical properties of the system, and this can be difficult. And most systems are too complex and have to be idealized to develop a traditional controller. What this means is that you don't have a full representation of the system when you design your controller. And the conditions when traditional controllers will work is usually fairly limited. Fuzzy logic controllers, on the other hand, you don't need to know much detailed knowledge of the system. And what the controller should do is determined by linguistic rules, and this is very easy to do for humans that know what the controller should do in certain situations. And if optimization tools are used like genetic algorithms, you can get away with not knowing much of anything about the system. The system also doesn't need to be reduced or idealized to develop a working fuzzy logic controller. And the conditions when fuzzy logic controllers will work are more robust because they can account for more variability in the inputs. So what is its potential? The number of applications are virtually limitless. You could have control systems like kitchen appliances. You could also have car control systems, aerospace vehicle control systems. Fuzzy logic can also do image processing, decision making, route planning, and it's still in development and testing for safety critical systems like autopilots, although it has been tested and implemented in some small instances like small satellite attitude control. But remember with fuzzy, the sky is literally not the limit.
From the video, hopefully you can understand much more better regarding the basic of the fuzzy concept. So now I will recap back a bit about the fact that has been stated in the video. So the second part is why we use the fuzzy logic. So this is almost the same examples from the car. So we have two persons here. The first person is the craftsman, and then the second person is the fuzzy man. So in general, craftsman will be relying on the singleton function, in which it need to rely on the facts in order to generate a sentence. So for instance, for the craftsman, it will state that how do you park your car? So you need to accelerate for 3 minutes and 46 seconds with some speed 25 kilometers and etc and etc. So in contrast with the fuzzy man just use the natural language that we usually use by human. So in a simple way, what the fuzzy man can say is that just move slowly back and avoid any obstacle. So this is the way how the fuzzy was different with respect to the crisp man. So what is the crisp man say is that this is usually done in computer thinking. Computer needs some objective, needs some values in order to generate things. In contrast with fuzzy will rely on the what we call as the natural language in order to generate its sentence to execute it task properly. So let's go for the second example. So in general, for who are you? Chris man will say 170 centimeters high, but for the fuzzy man, just a simple sentence of the tall person. So the same thing with the weather and etc. So weather for the crisp man will say 40 degrees, and then for fuzzy man straight away very hot, which is much more understandable by human. So how make the things fuzzy much more better in contrast with the crisp concept is that, so let's say for fuzzy man, for it can stated that it's very nice weather, means that it's not really sunny, be a bit cloudy. So, but for the crisp man, so you need to realize on some parameters. If the parameters is unknown, means that it able to make some decision. So in that case, so that's one of the case that the fuzzy concept will be a supersede with the general concept of the crisp man, or in general the digital notation in contrast with the fuzzy notation. So in general, you can think that the Crips concept is something like the digital concept, while the fuzzy is more on the a bit digital with surrounding by the analog probabilities. So fuzzy logic can do many things. So first thing first is it can represent the vague language naturally. Vague language is the way you speak So we use the vague language in order to ensure that what we speak will be understandable by people. So second thing is fuzzy is not replacing the crypt set. So means that in general, if you define some crypt function, so uh, let's say in a simple concept. So the crypts will be defined something like a singleton function with let's say 20. So the crypts will state that this is the highest probability of the occurrences. So in contrast, the meaning of this sentence, which is enrich not to replace the crypt set, means that instead of relying on the single crypt value, so it will expand the things into some probability of the occurrences. So this is where the fuzzy will enrich in terms of the notation of the dataset. So third things, the fuzzy can allow flexible engineering designs. Next, it will improve the model performance with proper tuning of the membership functions and the rule base. And then the fifth thing is simple to implement it because of once you have the foundation of the fuzzy, so you just need to replace or you need to do some try and error of the functionality or try to use the different membership function in order to tune the system properly. And usually fuzzy will works if you try that things in crypts notation. If it works, if you embed the fuzzy, it will usually work like the crypts configuration, but it will enrich a bit in terms of how the data was arranged or how the data was noted to ensure that the decision will be much more better. So the third part is how to use the fuzzy logic. So I will try to make the explanation much more simple using the very layman term so that you can understand the concept much more better. So basically, for every control system, so you will have some input with some controller, in this case fuzzy logic controller, and then the output. So this is the basic concept of every controller. Either you use it for the closed loop or for the open loop concept. So for the fuzzy logic controller, it comprises of four main components. So if we expand that thing, so fuzzy logic comprises of the four main components. So the first one is the fuzzifications. Fuzzification is the block module in which we will transform the crypts representation to the fuzzy representation because of every processing under the fuzzy platform will need to use the fuzzy representation. So there is the first step. So crypts value something like let's say 30 degree. So there is the crypts value. So we will transform that thing to the fuzzy notation but transform the 30 degrees into the membership function. So for the first step, which is the fuzzification is where you will transform from the crypts value to the fuzzy representation by using the membership function. So this is some of the example of the membership function in which for the crypts, each of the crypts value, so the dot line is the crypts value. So the fuzzy is the membership function that will surrounding the crypts representation. So there is the first part, means that transforming from the crypts to the fuzzy notation. So the second part is the rule base. Rule base means that how you're able to relate between your input and output by using the fuzzy notation. So usually the rule base will use a simple concept which is if else concept. So in general for this case the rule base has have 9 rules. So the rule is that if x is small and y is small, then z is small. So this is how we construct the rule base in an easy way. You just need to think how many inputs that you have and then how the input will be related to output. and how every parameters input will be connected in each other is either by using the AND notation or notation. So that is the second part of the rule base. So first part is the fuzzification, transform from the crypts to the fuzzy representation. Second part is the rule base, in which how you're able to relay between input and output under the fuzzy configuration. And then the third part is the inferencing engine. So if you see the block of the inferencing engine, it will receive input from two modules. The first one is the fuzzification, second one is the rule base. So inferencing engine is where it will mix up all the input from the fuzzification and the rule base, and then it will decide how many rules in the rule base that will be fire up. That is the first thing. Second thing is that it will concatenate all the rules that has been fire up. So in this case, for instance, we have 9 rules. So based on the input and the rule base, so inferencing engine decide that only 4 rules that will be fire up, in which we have some shaded area here. So this is the way this model will work. So it means that if you have, let's say, rule base has 16 rules, inferencing engine will decide how many rules that will be fire up based on the input from the fuzzification step. So the final module, which is the fourth module, is the defuzzification step. Defuzzification means that after inferencing engine decided how many rules that will fire and concatenate all the outputs of the membership function. So the defuzzification will transform the combination of the all outputs to the single value representation. In this case, Z, which is the crypts value, equal to 5.84. So because of all the things that we fed here is in the crypts representation, so the output shall be also in the crypts representation in order to ensure that the system can work properly. So this is the 4 main components of the fuzzy logics. So the next part is let's dig into the details for every of this module. So the first module is the fuzzification, in which how you transform from crypts to the fuzzy representation. I've mentioned that things we use the membership function in order to do the transformation. So how we construct the membership function. So first thing first is that let's look at this representation of simple membership function, which is defined as the hard-coded function. So for the hard-coded function, you can see from here. So for every value that is lower than 180, the probability will be 0. And then for every value that is higher than 180, the probability will be 1. So based on this representation of function, so let's say if we want to decide whether Ahmad is tall, whether it's true or false in general. So for this case, if the Ahmad height is 180, so in this case the probability is 1. And then if 140, then the probability is 0. So it's quite clear cut from this part, means that it's either to give you the 1 or 0 values of occurrences for the given input. So however, let's say if height of Ahmad is 179.5. So for this case, what is actually the height based on this function? So in this case, if we give the 0 occurrences, so means that we'll set that Ahmad is not tall, even though it just 0.5 offset with respect to the given value. So how we solve this thing? So usually we will define a soft membership function, in which we will define some high probability of the occurrences, and then we provide some much more soft representation for any value that is nearby the main part. So in this case, So let's say if we stated that this is the probability of tall. So in general, if we said that 180 is a 0.6 tall, so we can say that if the height is 179.5, so means that it is 0.56 tall. So instead of we give the zero occurrences. So the same thing with, let's say the height is 200, so means that we can say that is tall with the full probability, which is the high 100% of the occurrences. So the question is that how we decide or how we design the membership function. So in general, when we designing the fuzzy membership function, the usual function will be the triangle, trapezoid, and Gaussian. So that is the common things that you will utilize later on in your design. So what is a membership function? So membership function in a simple way is the 2D representation of the data in which in the y-axis y-axis is the probability of the occurrences. So because of this is the probability, the lowest value will be 0 and then the highest value will 1. So for this case, if all the value touch the 1, so means that we can say that this is the location where the data with the highest probability in the set. So in the x-axis is the universe of discourse. So universe of discourse in general is the collection of all the real values that you want to put in your membership function. So in this case, either is the voltage, speed of car, and error. So let's say, for instance, if we take some simple example of the speed. So let's say if want to say that this is the speed and then this is the probability of the occurrences 0 1. So if you want to define the membership function of fast, so let's say if you want to say 120 is fast, so we can develop the simple membership function that will define fast by using triangle, in which I can say 120 means that we have the highest probability, 100% is belongs to the fast. So let's say if we have 80, so let's say 80 for instance, so 80 is the 0 or 50% of fast and etc. So that is the beauty of the fuzzy concept, in which you will enrich the representation of the data in every in every different range of the given data set. So this is some example of the available membership function. We have the S function, pi function, triangle, trapezoid, and etc. We will focus on only some small part of the membership function in this class. So the first thing that we will look at is the trapezoidal membership function. So this is the example of the trapezoid membership function. So in this case is how we define the representation of this membership function. So for every membership function, you need to remember it consists of how many parts. So for this case, we have first part, second part, third part, fourth part, and then this is the fifth part. So it will consist of the 5 sections. So for every of this part of the membership function, so you have some range in which it will be occur. So for this case, alpha, for every alpha there is for every u that is less than alpha, the value will be 0. So in between of the beta and gamma, so it will be 1, and higher than this part will actually 0. So we have settled 1 3 5. So for part 2 and part 4, so in this case we have some gradient in which we need to define the function for this part. Say for the part 2, so for the second part, so let's say this is the part where we will put u. So if you want to get what is the value here of the occurrences, so we can simply take by using the triangulation concept, we can take the length of this part and length of the big triangle here in order to determine the value of t. So the value of t here is actually equal to, in this case, we have the u here, which is your universe of discourse. So the length of this part is u minus alpha over the length of this part is 1, and then the length of this part is beta minus alpha. So in which this is how we represent the value in part 2. So if you're quite confused, so in a simple way, this part is actually equal to 1, this part equal to beta minus alpha. So 1 over beta minus alpha will be equal the length of this part. So we have t over, in this case, is u minus alpha. So in this case, t equal to u minus alpha over beta minus alpha, which is the same to represent this part. So if we move on to for this part, which is the another gradient part. So for this case, if we put u here, so we can calculate in terms of the part t here. So since you are in the middle of the gamma and this part, so we can say that in this part is the sine minus u over the sine minus gamma, which is equal to t. So you have derived the membership function for this segment. So that is the simple way on how you are able to calculate all the function that represent the membership for every shape of the membership function. So the same thing with this part. Let's say it's quite straightforward. So this is the first part, second part, third part, and then fourth part. So the same thing. We segment the thing according to the value in the x-axis, and then later on we determine the gradient information. So gradient information here is for part number 2 will be simply mu minus a over b minus a, and then for number 3 for the gradient information will be c minus u over c minus b. So it's quite straightforward. So the third membership function is as membership function, but usually we will use in this class session for the calculation part, we will focusing on the two parts, either the trapezoidal or the triangle. So let's say for this exercise, the first question, write down the mathematical expression for the L membership function shown. So for this part, so first we need to determine how many segments. This is the first segment, second segment, and then third segment. So let's say if I develop this representation of f with respect to the universe of discourse. So we have three parts here. So the first part is what is the value if u less than alpha, and then what is the value if u higher than alpha, lower than beta, and then the third part is u higher than beta. So this one is straightway the value of 1, and then this is straightway value of 0. So for the center part, which is the second part of this membership function, so we can determine if we put u here. So the second part will be equal to, because we need to find the length of this part, so it will be equal to b beta minus u over beta minus alpha. So we have settled up to construct this membership function. So this is the first exercise. So for the second exercise is for this membership function. We have 1, 2, 3, 4, 5. We have 5 parts. So for this part, so let's say the same thing, function with respect to the universe of this course, we divide this thing into 5 parts. So based on the segment of that thing, so first is u less than -1, second is u higher than -1, lower than 2, next u higher than 2, less than or equal to 4, next u higher than 4, less equal to 5, next u higher than 5. So this one is 0, this one is 0, between 2 and 4 is actually 1. So this is equation number 2, this is equation number 4. So for equation number 2, let's see, I do that thing here. So equation number 2 will be equal to u minus 1 over 2 minus 1, which is equal to u plus 1 over 3. So this is for equation number 2. And then finally for equation number 4. So equation number 4 means that if we put u value here, so means that 5 minus u over 5 minus 4, which is 5 minus u over 1. So this is the way on how you're able to construct every part or every segment function for the given membership function. So that is the first part, which is the falsification. So the next part is the rule-based, how you're able to relate input and output. So as I have mentioned previously, so in a simple way, we will use the fuzzy if-then rules. So the if-then rules is the conditional statement. So in which is stated that if some fuzzy proposition here, then you have some fuzzy proposition at the output layer. So in general, after the if statement, so we call that thing as the antecedent, and then after then we call that thing as the consequent. So this is the premise in which how you relate between every inputs in your system, and then this is the conclusion, which is in the layman term. So this is the summation or combination of every input. So this is the part of the output based on the given input, and how you're able to relate that thing. So for instance, let's say if we have some simple notation, we want to relate between input of speed brake with respect to the gear. So in this case, if speed is high and brake is low, so speed is high, you drive a car in highways, your speed is high, and then you don't apply much brakes, then for this case, automatic gear should be high in order to ensure that it will run smoothly. So for instance, if speed is low and brake is applied many times or brake is high, then in this case, gear should be low. So this is how we usually construct the rule base. So in general, most of the things will be represented in the metric notation so that it will be easy to understand. So for the metric notations, so in the first section of the matrix, so this is your first input. Let's say I name it as input 1. So this is the part where the second input. So if we have here speed or brake, so in this case we have some error dot common temperature, and then there is another error. So the one that you fill up in the matrix is actually your consequent or your output. So every output lies out in the outside of the matrix. Whatever you fill up here is actually the output of your system. So input will located outside of the matrix, and then output will be located inside of the matrix. So the next part is the inferencing engine. Inferencing engine, as I mentioned, so it will process your input from falsification and rule base in order to decide which rule will be fire up. And then second thing is how we concatenate all the given output. So the fuzzy inferencing component is the rule base, which contain a selection of the fuzzy rule. So means that this is where it will decide. Let's say rule base has 9 rules, so it will select which rule should be fire up by given the input from the falsification. So it will be the same thing, almost the same thing with the role base, in which it consists of the database of the membership function, but this is the database that will be fire up. So this how it will decide that thing, it will be based on the connection of the input, the probability of occurrences of every input, and then based on the occurrences of every input, and then we decide how the output should behave with respect to the occurrences of the input. So for instance, if you have 2 inputs, so it will select based on the lowest probability of that thing, and then the probability will be tagged in the output layer. So I will show you the details later on. So this is some of the example how we do that thing. So let's say this is part where we have the rule base. So inferencing engine will decide which rule. Let's say you have rule 1 until rule R. So maybe rule 1 or rule 3 that will fire up based on the given input. So that thing will be decided by the inferencing engine. So in this part is the aggregator. Aggregator means that let's say we have decided only 2 rules that will be fire up here. So it will be concatenate the 2 rules here in order to develop some fuzzy model before the before we find the Cripps value. So the final part is the defuzzification. Is quite straightforward. Means that you have the representation of the fuzzy. So how we are able to transform that thing into the Cripps representation. So in this class, we will use 2 methods. The first method is called the center of the error. Center of error is the discrete method. Means that based on this equation, so the center of error method is something like the sampling, digital sampling process, in which you will define some digital part here based on the given resolution. So let's say every integer 1, 2, 3, 4, 5. So then after that it will calculate all the occurrences of this sampler. So it will be divided over all the sum up probabilities, so that you can find where in this part, it will lies the center of the area. So there is the center of area method. So means that the step is digital setting based on the given sample with how many resolution. So usually it will be integer resolution to make the things easy to calculate, and then later on multiply everything with its occurrences over all the sum up of the probability. So then we can get the output of the center of area. So the second method that we will learn is the bisector of area. So bisector of area is something like in general, based on this equation is because of we have some integration here, means that we find the area of that thing. So in general, in a simple things, a bisector of area, the first step is we calculate the whole area of this membership function that has been concatenated by inferencing engine. Next part is we divide the area into two, bisect the area. That is the mean of the bisector. We have the total area, bisect the area, means that divide the area into two. Then this length is where the value of bisector of area. So it means that we find the center of area by using the area. Sorry, by combining all the areas. In contrast with the first method, which is centroid of area, we sampling the things by using our sampler resolution, then we find the center of area. For the bisector of area, we find the whole area of that thing bisect into two, and then we find the center of area. The next part is let's design the fuzzy system to make the things much more easy to understand.